A data center relies on continuous, uninterrupted power. A fraction of a second of electrical disruption drops servers, halts transactions, and compromises data integrity. If the main incoming feed falters, the facility has to physically disconnect from the failing grid and draw power from a backup generator without the downstream load ever noticing. The intelligence directing that transfer is the automatic transfer switch, or ATS. Sitting between the two incoming supplies, it acts as the single supervisory control point. It evaluates incoming voltage, confirms the alternate source is ready, and dictates exactly which power path feeds the facility. To execute this safely, the system enforces a strict break-before-make sequence. The active source breaker, Q1, must open completely before the alternate breaker, Q2, is allowed to close. For a brief physical moment, neither source is connected to the bus. This physical isolation is engineered intentionally. It prevents the distinct electrical supplies from ever connecting in parallel, avoiding a catastrophic collision of out-of-phase power sources. The ATS enforces a controlled, transient blackout. The critical load only survives this intentional blackout because the uninterruptible power supply, the UPS, bridges the gap. The instant incoming power drops, the UPS discharges its internal batteries, maintaining a flawless sine wave to the server floor while the mechanical breakers transition. The ATS controller executes its logic rapidly, but that logic is a digital abstraction. The controller issues commands, but it is blind to the physical realities of jammed mechanisms or welded contacts inside the switchgear. Because of this blindness, human operators follow a strict 5-step protocol: authorize, verify, operate, confirm, and record. You must verify the actual physical states, the mechanical breaker positions, the true source voltage, and the UPS battery readiness. You do not rely solely on the digital panel indicators. Every button press on the controller must have a specific, anticipated electrical result. If you command a transfer, you must know exactly what physical actions the switchgear is about to take. The digital screen provides a map, but the physical switchgear is the territory. By confirming the mechanical reality of the system, the operator serves as the ultimate safety interlock, keeping the powertrain online. We rely on manual mode for authorized testing, commissioning, or controlled maintenance. It suspends automatic source priority logic and is never used for unprompted day-to-day operation. Starting from a stable grid on source 1, you press and hold the manual key to take control of the logic board. Once in manual, you select Q2, the standby generator, as your specific target source. Because this is a manual operation, the transfer does not execute automatically. You must physically start the standby generator and monitor the panel to verify source 2 has reached acceptable voltage and frequency limits. Once the generator is ready, you press execute. Breaker Q1 snaps open, and the UPS batteries take the critical load. The ATS validates the generator supply. With source 2 confirmed healthy, Q2 closes to lock in the generator feed, and battery discharge halts. The execution is only half the process. You must now confirm the physical result. Verify Q1 is open, Q2 is closed, and check the UPS screen to ensure it is accepting the new source and no longer draining batteries. Manual mode proves that safe operation is not a sequence of button presses, but a governed progression of strict physical verifications. Returning the facility to the normal grid follows the exact same discipline. You select Q1 as the target source, but you wait to ensure the utility grid, source 1, is fully stable and showing no active faults. Once confirmed, you command the reverse changeover. The sequence mirrors the initial transfer. Q2 opens, immediately cutting the generator feed. Again, during this open transition, the facility enters an intentional blackout. The UPS steps in, discharging its batteries to bridge the gap and maintain the critical load. Finally, Q1 closes, restoring the utility grid to the facility. With the load securely back on source 1, you initiate the approved generator cooldown procedure. Every controlled transfer relies entirely on the health of the UPS batteries to protect the servers from the harsh reality of the break-before-make sequence. For standard, unattended operation, the ATS remains in auto mode. In this state, the controller actively supervises the grid and uses source priority logic to respond to unexpected failures mechanically and immediately. If the primary grid fails at time 0, the UPS detects the drop in milliseconds and instantly shifts the load to internal battery power. But this creates a hidden electrical hazard. Because Q1 and Q2 are 4-pole breakers, opening them severs the neutral connection to the facility. This leaves the UPS input neutral dangerously floating while both source paths are open. To fix this, at time T1, the system activates a transient PEN bonding connection. The PEN contactor energizes to temporarily bond the UPS input neutral to protective earth, maintaining a stable neutral reference while Q1 and Q2 are open. This chart shows the outage timing sequence. From T0 to T3, the controller opens Q1 and signals the generator to start. From T4 to T6, after validating the generator, Q2 closes. The UPS halts battery discharge and the PEN bond safely releases. The data center survives grid failure exclusively because this 15-second sequence of battery discharge and neutral bonding bridges the mechanical gap between the two sources. Eventually, the utility company restores power to the grid. However, the ATS does not immediately switch the load back to source 1. This chart illustrates the restore sequence. To prevent dumping the facility onto a volatile feed, the system enforces a return stability timer to prove the grid is stable. Then, Q2 opens. The UPS bridges the gap, the PEN contactor cycles, and at T3, Q1 closes. The generator does not shut down the moment Q1 closes. A mandatory cooldown timer keeps the engine running without load, allowing internal temperatures to normalize before the final shutdown. The automated return logic proves the ATS is designed to strictly prioritize the safety of the critical load over rushing back to the primary utility. During any of these sequences, a breaker mechanism might fail to move, causing the transfer logic to hang and triggering an active alarm state. There is a dangerous misconception that pressing the digital reset key on the controller is the primary method for clearing the fault. Pressing reset without investigating the physical switchgear merely clears the digital latch. The physical hazard remains active, drastically increasing the risk of a catastrophic system failure if the controller attempts another transfer. You must execute a mandatory diagnostic workflow, read the alarm, record the system state, and physically inspect the switchgear to identify the blown fuse, control wiring fault, or jammed mechanism. You correct the root cause first. The reset button is purely an administrative tool. It is only pressed to clear the controller's logic board after the physical world has been proven safe. Every timer, interlock, and logic sequence programmed into the ATS exists for one specific purpose: to preserve the physical integrity of the facility's single-line diagram. The ultimate operator discipline required to support this architecture is strict. Verify before, observe during, and confirm after every single transfer. Execution is only half the job. Comprehensive logging of final breaker states, source conditions, and alarm history is required for troubleshooting and operational accountability. Safe operation relies on confirming the physical, electrical conditions of the switchgear, not on assuming the logic board's commands were actually executed. By mastering the electrical realities behind the digital panel, the operator guarantees the absolute continuity of the data center's powertrain.